This is the fourth video of chemical kinetics. In our previous videos, we have discussed rate of reaction, rate law and first order reaction. Today we are going to discuss zero order reaction. For example, there is a reactant A which converts into product. So when you write the rate law for this reaction, you will get rate of reaction is equal to rate constant multiplied by the reactant concentration raised to the power 0. As the order is 0, so the power is also 0. Now let's find out the unit of rate constant for zero order reaction. As we have already discussed, the rate of reaction can be expressed in terms of change in reactant concentration with respect to time. And reactant concentration is expressed in terms of molarity. So the unit of rate of reaction will be molar per second. Now place the values in this equation. Rate of reaction can be expressed as molar per second is equal to rate constant, and the unit of reactant concentration is again molar raised to the power 0. And as you all know, if any number x has power 0, its value is 1. So when you solve this equation, you will get molar per second is equal to rate constant multiplied by 1. That means the unit of rate constant you will get molar per second. Molarity is nothing but the number of moles per liter of solution. So molar can be expressed in terms of mole per liter, and here per second is there. So you will get unit of rate constant either as molar per second or moles per liter per second. Now come to the differential rate law. When you write the rate law for this equation, you will get rate of reaction is equal to rate constant multiplied by reactant concentration raised to the power 0. And rate of reaction can also be expressed in terms of decrease in reactant concentration with respect to time. So you will get another equation, rate of reaction is equal to minus dA over dt, as both the terms express the rate of reaction. So we can equate these terms and you will get another equation, minus dA over dt is equal to K reactant concentration raised to the power 0. And when you solve this equation, you will get minus dA over dt is equal to K. And this is the differential rate law for zero order reaction. When you integrate this differential rate law, you will get integrated rate law. So let's integrate this differential rate law. Before integration, you have to rearrange the equation. So when you shift dt on the right side of the equation, you will get dA is equal to minus k dt. I have also moved this negative sign to the right side of the equation. Now integrate this differential rate law under the limits a0 to at and 0 to t. We have the formula integration of dx is equal to x. So when you apply this formula on this equation, you will get a limit a0 to at is equal to minus k t limit 0 to t. Now apply the limits. So you will get at minus a0 is equal to minus k in bracket t minus 0. When you solve it, you will get at minus a0 is equal to minus kt. You may get another form of this integrated rate law by rearranging the equation. So let's rearrange it. When you transfer t to the other side of the equation, you will get minus k is equal to at minus a0 over t. Now multiply this equation with minus. So you will get k is equal to a0 minus at over t. This is the another form of integrated rate law for zero order reaction. Now come to the graphical representation of zero order reaction. We have the equation rate of reaction is equal to rate constant multiplied by the reactant concentration raised to the power 0. That means rate remains same even on changing the reactant concentration. So when you plot graph of rate versus concentration of reactant, you will get a straight line that is parallel to the x-axis because rate doesn't change even on changing the reactant concentration. Now come to the another graphical representation of zero order reaction. So we have the equation AT minus A naught is equal to minus KT. Now transfer this A naught term on the other side of the equation as it is negative in this side. When you transfer this term on the other side of the equation, it will become positive and you will get AT is equal to minus KT plus A naught. Now this equation can be compared with a straight line equation, that is y is equal to mx plus c. Now compare both the equation. So you will see x can be compared with the time. So I have plotted time on the x-axis and y can be compared with the AT. So I have plotted AT on the y-axis. Here you can see intercept is compared with the A naught. That means C is not equal to 0. That means a straight line will not originate from the origin. It will originate from somewhere on the y-axis. And slope is negative. That means the straight line that you will get will have some negative slope. So you will get a straight line, descending straight line with the slope minus k, and the intercept will be equal to A naught. Now come to the half-life of zero order reaction. Half-life is defined as the time required to consume half of the reactant. Example, there is a reaction in which reactant A converts into product. Initially, at time t is equal to 0, initial concentration of A can be represented as A naught and it is equal to A. The time at which half of the initial concentration of reactant has consumed is known as T half. And at that time, AT will be equal to A by 2, that is half of the initial concentration. So we have all these values and we have to place these values in the zero order equation. That is A is equal to A naught minus AT over P. We have the value AT is equal to A naught over 2 and T is equal to T half. So you will get the equation A is equal to A naught minus A naught over 2 divided by T half. When you rearrange this equation, you will get T half is equal to A naught minus A naught by 2 divided by K. When you solve this equation, you will get T half is equal to A naught by 2 divided by K. When you rewrite it, you will get T half is equal to A naught over 2K. This is the half-life period for zero order reaction. Half-life of zero order reaction varies on changing the initial concentration of reactant, as this equation involves initial concentration of reactant. In the next video, we are going to discuss collision theory and Arrhenius equation.